Hello students, this week we will cover the binomial probability distribution. Our objectives are to determine whether a probability experiment is a binomial experiment, compute probabilities of binomial experiments, compute the mean and standard deviation of a binomial random variable, graph a binomial probability distribution. The criteria for a binomial experiment is as follows. An experiment is said to be a binomial experiment if 1. The first condition, the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. The second condition, the trials are independent. This means the outcome of the one trial will not affect the outcome of the other trials. The third condition, for each trial, there are two mutually exclusive or disjoint outcomes, success or failure. Number 4, the probability of success is fixed for each trial of the experiment. There are some notations that will be used in the binomial probability distribution. We're going to use n to represent the independent trials of the experiment. We will be using p to denote the probability of success, so the probability of failure is going to be 1 minus p, which is the complement of the probability of success. Let x be a binomial random variable that denotes the number of successes in n independent trials of the experiment. Then x is going to span between 0 and n, meaning we can have 0 successes through n successes in total. Let's look at some examples and determine whether they represent a binomial experiment or not. The first example, we have a player rolls a pair of fair die 10 times. The number x of 7s rolled is recorded. So in this case, we notice that the experiment is performed a fixed number of times. The trials are independent because when the player rolls the first time, it doesn't affect the outcome of the second time the player rolls the die. We notice also that the events are mutually exclusive, meaning if the player gets a 1, then that is the outcome. The player cannot get 1 and 5 at the same time because the player is rolling one fair die. The last condition, let's see if it's met. The outcomes are equally likely to occur because rolling a die is going to give you an equally likely outcome, and that is 1/6 for each face. So we can say the probability of success is fixed for each trial. And because it meets the 4 conditions of a binomial experiment, we are going to say this is indeed a binomial experiment. Let's look at another example. The 11 largest airlines had an on-time percentage of 84.7% in November 2001. According to the Air Travel Consumer Report, in order to assess reasons for delays, an official with the FAA randomly selects flights until she finds 10 that were not on time. The number of flights X that need to be selected is recorded. In this case, we don't have a binomial experiment because the number of trials is not fixed. In this case, she selects flights until she finds 10 flights that are not on time. She could find that in the first 10 flights, she can find that in the first 50 flights, she can find that in the first 100 flights, no one knows. So since the number of trials for this experiment is not fixed, this is not a binomial experiment. Let's look at another example. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. This experiment is not going to be binomial because the instructor randomly selects 4 students and the trials are not independent. So if the instructor selects the first student, that is going to affect the second time the instructor selects another student. So the trials are not independent and the experiment is not a binomial experiment for that reason. Let's look at an example of how to construct a binomial probability distribution if we are using the tree diagrams. According to the Air Travel Consumer Report, the 11 largest air carriers had an on-time percentage of 79% in May 2008. Suppose that 4 flights are randomly selected from May 2008 and the number of on-time flights X is recorded. Construct a probability distribution of the random variable X using tree diagram. So in this case, if we use tree diagrams, what are the possibilities for those 4 flights? The possibilities are, we're going to have the first flight on time or not on time, so we have success or failure. And then the second flight, if the first flight was on time, the second flight could be on time or could be not on time. If the first flight was not on time, the second flight could be on time or not on time. And then we go to the third flight. Again, if the first flight was on time, the second flight was on time, the third flight could be on time or not on time. If the first flight was on time, the second flight was not on time, the third flight could be on time or not on time. Similar for the failure. So if the first flight was not on time, the second flight was not on time, the third flight could be on time or not on time. If the first flight was not on time, the second flight was not on time, the third flight could be on time or not on time. Similar for the fourth flight, so it could be not on time or on time for all of these branches. So we will have all of these possibilities. So the possibilities are all of the flights are on time, or the first three flights are on time, or the first 2 flights are on time, the third is not on time, and the fourth is on time, and etc. So you know what this means. Now, the possibilities that we see are, we have the X here and we have the probability of X. We have the X, which is the flights. We are selecting 4 flights, so we can have 0 flights on time. We can have 1 flight on time. We can have 2 flights on time. We can have 3 flights on time, according to the numbers that we see here and we see here as well. So if we want to find the probability that the flight was not on time, none of the flights was on time, so the probability of 0, none of the flights was on time, we have the last option, which is all failure here. So that is the probability. In order to do that, we're going to multiply all of these probabilities. Remember how we built the tree diagrams with probabilities? So the first, we know that the chances of success are given in the question, which is 79%. That means the failure, 1 minus p, is going to be 1 minus 0.79, which is equal to 0.21. So that is the chance of failure. So if we plug these numbers in here, we will have 0.21 for the first one, 0.21 for the second one, 0.21 for the third one, 0.21 for the fourth one. Now the probability of failure is going to be the probability that the first one failed to be on time, and the second one failed to be on time, and the third one failed to be on time, and the fourth one failed to be on time. Since this is a binomial experiment, we know that trials are independent, and as a result, we're going to say this is just the multiplication. We're going to use the multiplication rule since we hear the word and. So we're going to multiply all of the probabilities together, and we're going to get 0.00194. Usually we round to 4 decimal places. And we will continue with the rest of them. So if we're talking about the same branch, we're going to multiply. If we talk about the same branch and then we talk about another branch, we're going to add the probabilities together. Let me show you what I mean. If we wanted the probability of one flight is successful, we have many options. We have the first flight is successful, or the second flight is successful, or the third flight is successful, or the fourth flight is successful. So all of these are going to give me the probability of one flight is successful. How do I compute it? I'm going to compute each branch, multiply, and then add those branches up, because I'm going to say it's going to be success. It's going to be either the first flight is on time, but the rest are not on time, or the second flight is on time, or the third flight is on time, or the fourth flight is on time. Because I'm using or between the branches, I know I'm going to add these branches together. When I talk about each branch, I say the first flight is successful and the second and third and fourth are not successful. So I'm using and when I talk about one branch. That means I'm going to use multiplication when I talk about one branch. Let's find the probability of the first branch. The probability of the first branch is success, which is 0.79, failure 0.21, 0.21, and then 0.21 for the last one because it's failure as well. Now multiply them all together, you will get the first part. And then plus the second branch. This is my second branch over here. So failure 0.21, success 0.79, failure 0.21, failure 0.21, which is going to give me the second branch over here. And then plus the third branch. This is my third branch over here. So failure 0.21, 0.21 times 0.79 times 0.21 in this branch. Plus the last branch, which is this one over here. That is 0.21 times 0.21 times 0.21 times 0.79. I'm going to get that answer. Now, this is a dreadful process. It's very hard to find out the answer that way. It will take me forever to compute all of the binomial probability distribution. So conveniently, we have a formula to compute all of that. So instead of building this tree diagram and creating the binomial distribution table like this, we can actually compute the binomial distribution and build the binomial distribution table in an easier way. Let me show you first the formula for the binomial distribution. So the binomial distribution says the probability of x is equal to the combination of n, choose x, p raised to the x power, the probability of success raised to the x power, times 1 minus p raised to the n minus x power. So for the previous experiment, to compute one of the probabilities, let's say the probability of 1 is equal to, it's going to be, we have n, which is, we're going to say we have n is equal to 4, so 4 choose 1. I'm going to write it like that. You can write it like that as well. And then the probability of success is 79 raised to the 1 power, which is the x. And then I'm computing here. This is x is equal to 1. This is n, and this is x is equal to 1. Times the probability of failure 0.21 raised to the n minus 1, which is 4 minus 1. And that is the answer. So if you find this computation, you can use the calculator to compute the combination here, or you can use Excel. We're not going to use the formula either. The formula is very painful to do. So we can do the binomial distribution. We can create and build binomial probability distributions on Excel using the function binom.distribution. So the function is equal to binom.dist. And then you select your data and the other information that you need to plug into your formula. Here are some phrases that are important when dealing with binomial probability distribution. Here is an example to apply in the formula. Remember that we're not going to use the formula, but I would like to show you how to use the formula to compute the binomial probability distribution, just in case. According to Experian Automotive, 35% of all cars owning households have 3 or more cars. In a random sample of 20 car owning households, what is the probability that exactly 5 have 3 or more cars? So in this case, we know that the n, the sample size is 20, n is 20. We know that the probability that a household, the probability of success, that is a household owning 3 or more cars, is 35%, which is 0.35. So the probability of failure is 1 minus p, which is 1 minus 0.35, and that is equal to 65. 0.65. The next thing we want to determine is we want to find x. In this case, we want the probability that exactly 5, so x is equal to 5, have 3 or more cars. So exactly 5 households have 3 or more cars. To compute that, we have x, we have p, we have n. We're going to apply that to our formula. So the formula, to remind you, it says n choose x of the probability of success raised to the x power times 1 minus the probability of failure n minus x raised to the n minus x. This is the probability of x. So the probability of 5 is going to be, we remove the x and n, replace n and x into our formula. We will get 20 choose 5 of 0.35 raised to the 5th power times the probability of failure, which is 0.65 raised to the 20 minus 5, which is 15. Then you compute that on Excel or using your calculator, and you will end up getting this number. Remember, we're not going to use this when we compute the probability, the binomial probability distribution. We will do it in an easier way. Then if we want to find the probability that in a random sample of 20 cars owning households, what is the probability that less than 4 have 3 or more cars? We want the probability that x is less than 4. So that is the probability of 0 households have 3 or more cars, or 1 household have 3 or more cars, or 2 households have 3 or more cars, or 3 households have 3 or more cars. Because I'm saying or, I'm going to add all of these probabilities up. And you guessed it, we're going to use the formula to compute each of these probabilities. You see how hard that is? So in order to do this, we can do it easier using Excel. The mean and the expected value and the standard deviation of a binomial random variable. The binomial experiment with independent trials and probability of success P has a mean and a standard deviation given by the formulas. You need to write down these formulas because those are the formulas we will use to compute the mean and the standard deviation. The mean, or the expected value, is the number of trials times the probability of success, and the standard deviation is the square root of the number of trials times the probability of success times the probability of failure. So that is how you're going to compute the mean and the standard deviation. I'll show you an example how to compute the mean and the standard deviation. In this example, according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. In a simple random sample of 400 car-owning households, determine the mean and the standard deviation number of car-owning households that will have 3 or more cars. Here we need to determine n, we need to determine p, and we need to determine 1 minus p. So in this case, the first thing is the probability of success is 0.35, which is households that have 3 or more cars. And then the probability of failure is 1 minus p, which is 1 minus 0.35, 0.65, or 65%. Then we need n. We know that the random sample is, or the sample size is 400, so n is equal to 400. Now we're going to use the formula. To find the expected value or the mean, we're going to use this formula. So we're going to multiply n times p, which is 400 times 0.35, which will give us 140. To find the standard deviation, we're going to take the square root of n times p, which is 400 times 0.35 times 1 minus 0.35, which is 0.65. You multiply first and then take the square root. You will get this answer, 9.54. So this is how you're going to compute the mean and the standard deviation for a binomial distribution. In the next video, I will show you some examples on how to compute binomial distribution and create a binomial distribution table on Excel and find the answers easier than that. And I will show you another example on how to use Excel to compute the mean and the standard deviation. We're still going to use the formulas, but it's easier to work on Excel since you have the calculator right in there. So I'll see you in the next video.